mechanisms and predicting a mechanism, trying to elucidate what a mechanism that makes sense. Realize you can follow a mechanism that's showing all the arrows, right? And you're showing transition states that are low in energy, which is what we're trying to do. But experimentally, you have to test these. So you should be able to look at any reaction and come up with a reasonable mechanism based on what we know about our energies of our intermediates, what we know about drawing our arrows, and it takes practice, and you need to learn the basics before you can do it. But there's sometimes you can draw a mechanism that follows all of that, and then experimentally you don't see those as products. For example, the difference between SN1 and SN2, which we can see clearly based on experimentation, the difference in things like stereochemistry. There's different ways to test mechanisms once you've come up with a reasonable one, like kinetics. There's a lot of different experiments. Most of the reactions that we talk about in the book have mechanisms that have been studied thoroughly, so we accept those mechanisms as most likely. But there are things that can happen to a molecule to make them go through a completely different mechanism. There is a mechanism called an E1CB. And E1CB is an elimination reaction, but it involves a conjugate base, where your pi bond actually gets attacked by the nucleophile first, leaving a negative charge on the carbon. And then the carbon acts as a base and protonates. We don't see this normally, and we don't teach it because a carboanion is really unstable. So this will only happen in a molecule that has something stabilizing the negative charge that's attached on the molecule, like a lot of electronegative groups that would stabilize the negative charge. Or the negative charge would be in resonance, a very stable resonance structure. So in most substrates, you'd never see the E1CB competing mechanism because a negative charge in a carbon is just not going to form because that carbon double bond is not polar. So it's very specific to very specific substrates that would stabilize the negative charge strongly. So it's not something we see very often. So we don't teach it because we're really teaching in here our most common reactions. A lot more reactions that happen that are similar but go through different mechanisms because of the other things going on in the reaction. So what we usually focus on are molecules that don't have a lot of other things that are going on, and we focus on the functional group itself. So keep that in mind when I'm talking about this and when I'm lecturing on this mechanism. Keep in mind most of the mechanisms we talk in class have been studied with experimentation thoroughly, so those mechanisms are fairly accepted for most substrates. But other substrates might go through different mechanisms. So first we're going to talk about a reminder on electrophiles and nucleophiles and what a mechanism is. Remember, a mechanism allows us to map out the movement of electrons in a chemical reaction. That's our purpose of a mechanism. It helps us to understand the products that we're seeing and helps us to predict products if we're using a completely different substrate. Like, we draw the mechanism, see a carbocation, and then we can see if there's a rearrangement. That's going to tell us if what our predicted major products are going to be. Before we get in the lab and we waste our time doing a reaction that's going to give us 10 different products, a big mess. That's not going to be helpful. So we're trying to avoid that. So we're mapping out our movement of electrons, and remember, these are ionic mechanisms, meaning we're usually forming some sort of either full charge in our intermediates or charge in our transition states. So we are showing the movement of 2 electrons. So if one atom gives up 2 electrons and it was neutral, it's going to leave it with a charge. Remember, electrons are negative, so it's going to leave it with a positive charge because it lost its 2 electrons. So that's our ionic mechanisms, mostly in organic chemistry. Chapter 11, we're going to talk about radical mechanisms, which are going to be slightly different than what I'm talking about here, but not hugely different, and when we come to it, we'll talk about it. They show the breaking of sigma bonds, the breaking of pi bonds, the forming of sigma bonds, the forming of pi bonds. They also show lone pairs being taken from isolated on one atom to being shared in a covalent bond. So that's what we're looking at. It helps us to do all of this. And also, remember, our mechanism arrows are used to represent resonance. Remember, that doesn't depict the movement of electrons, just allows us to understand how they're shared better for resonance. But most of the same rules apply with resonance. When we're writing a reasonable mechanism, we should always be following what's likely to occur in nature. So that's why we talk about these stability. We really focus on stability of things. We talk about those reaction coordinate diagrams. If you draw a transition state that's really unstable, remember, that's going to be a really high activation energy. That's not a reasonable mechanism. So your arrows are representing those transition states as well. Oftentimes, if we have too many arrows, that's going to be too high of a transition state. That's unlikely, so that would be unreasonable. So we're using these natural rules. If we take something, put it in a reaction mixture, we can sometimes use heat and pressure to force something to happen that doesn't want to. But we can only do so much. Our molecules are going to react with what's easiest. If we have a reaction that's a really strong nucleophile but also a base, then it's reacting with something that has both an electrophilic center and an acidic proton. It's always going to react with the acidic proton because it's easier to get to the acidic proton. So we're always considering that. So it helps us predict mechanisms and helps us predict what's going on. It helps us follow when we get a weird product, so where'd that come from? And then if you look at the mechanism, it usually makes sense. So even if you've never seen a reaction, you should be able to predict a mechanism. For the test, I will often ask you mechanisms that we've talked about, though they might be slightly different because the substrates are different, but usually the same basic mechanisms. However, it's really a skill to be able to look at any reaction and predict a reasonable mechanism. So remember, we're looking at ionic reactions and how they work. So our basis of the mechanisms are opposite charges attract. Electrons are negative, they're going to be attracted to a place of positive charge. Our other thing is that we're trying to follow the octet rule. So our mechanism should never represent an atom in the second period forming more than 8 electrons. So we don't really deal too much with atoms in the third period. And atoms in the first period, they only want to talk about hydrogen, and they can't have more than 2. So we're following those rules as well. So we're following the rules of opposite charges attract, and we're following the rules of the octet rule. If something is an electrophile, it has to be able to accept electrons. We're following what we learned about positive and negative charge and polarity. So for example, most of the time our carbon is neutral or partial positive. Because most of the time, our carbon is bound to things that are the same, that it's about the same electronegativity, where we consider this non-polar, or things that are more polar than it. Because usually we're working with carbon and everything to the right. But there's a couple of reagents we'll look at, like this one, where carbon is bound to lithium. Technically, this is an ionic bond where carbon's negative and lithium's positive. Their difference in electronegativity is kind of that gray area between ionic and covalent. As soon as you see this, you should think, well, this is partial positive. It's metal, so this is partial negative. You're just using that simple polarity that you've learned. You're applying it to any reagent. If you see this, then you're going to know that this is a source of electrons. So you should be able to use your simple electronegativity. You learned this in general chemistry, what we learned in chapter 1. And your polarity to figure out where reactions are going to occur and where we have a place for electrons, where we have a source for electrons. So first off, atoms that carry a formal or partial negative charge and have available electrons, or what we call nucleophiles, or electron sources, which really encompasses more than just nucleophile. Typically, nucleophiles can attack the electrophilic center versus a base acts very similarly, but it's only when it reacts with a hydrogen. Hydrogen's smaller, so we don't usually have sterics to consider. Electron source isn't specifying how it's reacting, it's just specifying that it's a source of electrons. So in a lot of older books, instead of nucleophile, you'll see the term electron source. This is a source of electrons that it can give up to do something. So technically, this has a lone pair. This is a carbanion, so C negative with a lone pair. The only other one that we really are looking at is a pi bond. We have available electrons even though it doesn't have a lone pair. So we have to have electrons available. So in these cases we do. Now note, just because a molecule has an electron source doesn't mean it can't also act as an electrophile. So I'll go back to that in a second. An electrophile is a place that wants electrons. Electrophile means electron loving. It doesn't have enough electrons, it wants more. So our partial positive carbons and our positive carbons are always electrophiles. Also our partial positive protons and positive protons are, of course, electrophiles. So those are acid-base reactions. They can accept electrons, so that's what we're always looking for. Whenever we have a reaction, even if we've never seen it, we should first find our source of electrons and find our place electrons can go. So sometimes electrophiles are called electron sinks because you can put them in there. You can put electrons in them. They can accept them. Now note, this is a nucleophile in that it has a lone pair. This is also an electrophile in that we have a partial positive carbon. So alcohols can act as electrophiles in the presence of something that's a nucleophile. Or alcohols can act as nucleophiles in the presence of something that's an electrophile. So sometimes we do have compounds that have both sources of electrons and places electrons can go, so it's dependent on what we're reacting them with. So we have to both look at our substrate and our reagents that we're adding in. How will it react? Now this, even though we have a partial positive carbon, is unlikely to ever act as an electrophile because this is already negative, so it's going to repel any electrons that are trying to come to it. Also, for an electrophile to attack this, we have to have a leaving group, otherwise it would have 5 bonds to carbon, and that would leave us O-2, very unstable. So again, that's following based on our activation energy, really unlikely to happen. So this would not be an electrophile. But this one could be because OH minus could leave in the right conditions. If we have the right conditions, we can have that occur. So note, just because something has a source of electrons doesn't mean it can't also have a place electrons can go. So you have to look at every case. Also, if we look at this guy, I don't know why it didn't. That oxygen, this whole molecule is an electrophile. But the place where the attack is going to occur is on the carbon. Because we can't attack that hydrogen. We can't attack that oxygen. Because that oxygen, even though it has a positive charge, already has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So for the oxygen to accept electrons, it has to break the bond. But the only things that could break is this sigma bond, this one, or this one, and none of those are good leaving groups. So even though this whole molecule is an electrophile, the place where we're going to attack is the partial positive carbon. Even though this is a full positive, it's still electronegative. This is still electropositive based on just our electronegativities, which is inherent of the atom, not of its overall charge. So our attack occurs here because this is a great leaving group. So just because there's a positive charge at a certain position doesn't mean that's the position that can't accept electrons. It does accept electrons eventually because it leaves with them, but our nucleophile, or our electron source, is going to attack the partial positive carbon. So now the next thing we need to do is remind you what our arrows mean. Because our arrows mean something. It's just like if you saw a stop sign, it means stop. It doesn't mean go, it means something. Our arrows mean something. It's just like a language. Someone reading the arrows, not talking to you, should be able to read your mechanism and know what they mean. So what our arrows mean is the base of the arrow is representing where electrons are coming from, which means your arrow can only start on a source of electrons. A sigma bond, a pi bond, or a lone pair. It has to be a sigma bond, a pi bond, or a lone pair that has electrons to give. So a carbocation doesn't have electrons to give, but also this oxygen, while it has a lone pair, does not have electrons to give. If it gave up those electrons, that oxygen would have +2. +1 is unstable enough for our oxygen. +2 would be too unstable. So not available. Just because something has a lone pair doesn't mean the lone pair is available. It has to be available. And our head of our arrow shows where the electrons are going, which means it has to be a sink, a place that can accept electrons. Could be a place of low electron density, a partial positive. It could be a anti-p orbital, or you could be showing it forming a pi bond. So we could show these. So our double head represents the movement of 2 electrons, which is what we're going to be talking about today. We're going to learn about radical arrows later on in chapter 11, which represent the movement of 1 electron. So remember, each arrow represents the movement of 2 electrons. So we use arrows to show how electrons move when bonds are breaking and forming. And there's some 4 main ways electrons move, and you don't have to memorize them, but it helps to recognize them, especially when you're putting a mechanism together, to kind of think about what's going on, but you by no means need to memorize them. So in a nucleophilic attack, something that has a lone pair that they can give up forms a new bond between something that can accept the electrons. So what this arrow is showing is that the bromine had this lone pair only associated with itself. But now, what we're showing is we're forming a covalent bond between the bromine and the carbon. And remember, this is organic chemistry and we're forming covalent bonds. So we're not showing an arrow to show that the bromine is throwing its 2 electrons onto the carbon and not forming a bond. It's trying to form a bond. There's a different type of chemistry where electrons are spontaneously given up, and we're not doing photochemistry. It's a whole different thing. Different set of conditions, we're not doing that. So I'm not teaching you that type of chemistry. I don't even think I really could teach you that kind of chemistry. It's kind of over my head. Ooh, I don't know what it is. I've learned it, but Very important, though, to things like solar cells. We're not going into that. So what we're forming is a bond between bromine and carbon. That's what our arrows show. That's what our product, that we are our intermediate. So this could be an intermediate and a mechanism. But this is what this should show. Whatever those arrows are showing, this should represent it. If you want this to occur but your arrows are not representing that, then that's not right. For example, I could technically show my deprotonation and forming of a pi bond. But this doesn't show a pi bond. This shows a bond between bromine and carbon. Your mechanism should represent, not only should it follow all the rules, it should also represent the actual thing you drew. That tells me what that is. So you have to be careful there. There's nothing wrong with the arrows I just drew, but it doesn't show the product that I'm showing. So notice our tail of our electrons are starting in a place that has electrons, and it's going to a place that can accept it. If you're drawing it coming from a lone pair, really, it's best to draw a lone pair. Old books sometimes don't, but it's better. It makes sure that you're counting for all your electrons. It's really specific that the electrons are not coming from the nucleus, which we know the electrons are not in the nucleus, so you're being specific there. Here, we're still getting a nucleophilic attack, but in this case what we're showing is the oxygen's lone pair, which is only associated with the oxygen, is now being shared between the oxygen and the carbon, forming a new bond. And then we can't have 5 bonds to carbon, so the pi bond is being pushed onto the oxygen. That makes sense because our oxygen is electronegative, and it can stabilize electrons. So based on just our energies, this makes sense. We have that polarity, we have that partial positive carbon. We form this transition state. That leaves a positive charge in the oxygen. Another thing, when you're drawing a mechanism, if you end up with a formal charge, you must specify it. It will be wrong if you don't show this positive charge. Also, we're left with a negative charge here. We'll learn that this is a high energy transition state, but under the right conditions it can form. So this is still a nucleophilic attack. There are things we can make this reaction go faster, but this is still a nucleophilic attack. Also, notice my arrows are representing my product that I'm showing, well, my intermediate product. Loss of a leaving group, something is leaving with electrons. This particular reaction is showing the bond between carbon and bromine is breaking. Bromine's taking the 2 electrons. That leaves the carbon with 2 less electrons than it started with, so it has a positive charge. You must show that carbocation. Very important. This might happen in 2 steps, like this proton transfer. In this proton transfer, we do have the loss of the leaving group occur as well. Again, notice here, our place that has available electrons is this guy. Our chlorine doesn't have available electrons until it leaves with a negative charge. Because if our HCl attacks something, let's say, I don't know, it just attacks something. I don't know what. Let's say it attacked here. That would form this. And that would leave my chlorine with a positive charge. That's pretty unlikely. So instead, the part that can react is our proton. That's where our reactivity is. Also, we'll often call something being deprotonating when our substrate is having a hydrogen being removed. Now again, the oxygen of water cannot directly attack our oxygen. It's really unlikely. Instead, what's much more likely is it will attack the partial positive hydrogen and push the electrons onto our positive oxygen. You might need multiple arrows for some of these reactions. This particular multiple arrow is just representing resonance, and honestly, showing this or showing this followed by these 2 resonance structures are both fine. This is just representing right away drawing our most contributing resonance structure, because if we're comparing these 2 resonance structures, this one's most contributing because the negative charge is on the more electronegative oxygen. When you're drawing a mechanism, you can show either of these steps. You can show it all happening like this and just show your more contributing resonance, or you may show the formation of one resonance structure and the other. If within your mechanism you're showing a resonance, you do want to put that in brackets. That's just representing that these are 2 resonance structures. Which is best? It depends what mechanism you're looking at. So, again, it just depends what you're using the mechanism for to see. So both of these are acceptable. This one's acceptable with all these arrows because this is just representing resonance. This arrow is representing the reaction. These 2 arrows are just representing the resonance. So either way is fine. If you rather draw this exactly and then draw your 2 resonance structures, that's fine. You can do that. You should recognize, though, that this negative charge is in resonance. Otherwise, this hydrogen would not be nearly as acidic. Hyperconjugation, like induction, can stabilize our carbocations, remember? So we could have rearrangements. If we're going to form a more stable carbocation, we will. These are intramolecular because it happens within the molecule, which means it's fast because 2 molecules don't need to bump into each other. They're already stuck together. However, we really only see this happening with neighboring carbons because they have to be close enough together to react. So that's what we'll see. So we talk about rearrangements a lot. I'm not going to focus on this too much in this particular. But you should always watch out for rearrangements. So looking at this mechanism, we have the arrows drawn. Convince yourself that each arrow shows the formation of the next thing drawn. This shows the bond forming between oxygen and hydrogen. and then bromine leaving with these 2 electrons. This is what we have. Now we're not even showing the Br negative, sometimes we don't. Then this shows the loss of water, oxygen, this OH2 plus, our oxonium ion, takes the electrons to form water. This negative charge isn't a negative. That's why I say circle your negative and positive charges. This is a minus, meaning water is leaving. Sometimes you'll see that. To avoid confusion, you don't have to draw it like this, but to avoid confusion, always circle your formal charges. Okay, it's very clear that this is a formal charge. So that leaves a positive charge on our carbon. Remember, this only had 1 hydrogen attached. This should still only have 1 hydrogen attached. If you don't show that positive charge, that represents that there's 2 hydrogens there. And we didn't show a hydrogen forming, a hydrogen-carbon bond forming, so there's no hydrogen-carbon bond forming. We must show the carbocation. Very important, especially when the formal charge is on carbon, because we don't show the hydrogens. Then we can have a rearrangement, and then we can have our nucleophilic attack. And just as the bromine is only shown in this step, it's there. Because remember, this isn't a reaction mixture. So everything's in this reaction mixture. This bromine didn't react with yet, it's still there. And there are, in the reaction mixture, multiple compounds going through each of these steps at once. Remember that. We're only representing 1 molecule of this thing, but the reaction mixture has multiple. So you might have multiple patterns happening at once, like our nucleophile attacking followed by the loss of the leaving group and this SN2 mechanism shown here. So a couple of rules to follow when drawing reasonable mechanisms, and then we'll go through some very common mistakes. And I think seeing the mistakes really help. And again, this pushing electrons, when we show these mechanisms, we call that electron pushing. I put this up, and it's very useful. I'm not going into resonance. It does go into a part about resonance, so you can go ahead and read that. We're going to really focus on the common electron pushing errors in here. And this particular document calls them electron sources and sinks. So that's a really common terminology, and I like that terminology because it's very specific. A source of electron. Nucleophile, sometimes students forget what that means. Source of electrons is very clear. So I like that terminology. So this is pretty easy to follow. Some of the examples at the end are pretty detailed and kind of more complicated. And it also goes into radical electron pushing, which we'll talk about in chapter 11. So this is a useful document. It does come from an advanced book, but it's basically a book that is assuming you've taken organic chemistry, so this is a review on how to do this in advanced chemistry. So this is stuff after you've taken organic you should know. So it's still acceptable for your level, for the most part. So remember, our arrow is starting in a source of electrons. So a bonded pair or a lone pair, like this example. It's incorrect not to show your lone pair. So show your lone pair. It's a lot more clear. So this arrow is incorrect because the chlorine is taking the electrons from the bond between carbon and chlorine. So that's the electrons that we need to show the chlorine taking. So it needs to be on the bond, not on this carbon. This carbon is not giving up the electrons. There's no lone pair on the carbon. It's the actual bond between the carbon and chlorine that's breaking. So that's where our base of our arrow should be. So this would be more clear. Except for this isn't clear because we have a positive charge on that oxygen. That oxygen, like I said, it might have a lone pair, but they're not available. Because what would form an oxygen 2+ is really unlikely. That would be too high in energy. So we won't have a tail of our arrow on a positive charge, on an atom with a positive charge. Because if it has a positive charge, it's holding those electrons close. Even if it has a lone pair, it's not going to be reactive. Especially not a carbocation, because that does not have a lone pair, no available electrons. The arrow ends on a nucleus, forming a new bond between that atom that has a source of electrons and the carbon, or it can end on a nucleus representing a breaking of a sigma bond that's now only going to be associated with the chlorine. So again, what this is showing is we're forming a bond between oxygen and carbon. That's this bond. And then this bond is breaking, so that carbon no longer has those two electrons. It's no longer associated, but the chlorine takes both of them. So we're representing that. Avoid the breaking the octet rule. This breaks the octet rule because we're showing a new bond between oxygen and carbon. That means carbon's now going to have 10 electrons. But we're not showing another bond breaking. You must show another bond breaking if it needs to. So that would not happen. So we must show that chlorine taking those electrons for this to actually be the mechanism. So don't break the octet rule. A common mistake, losing hydrogens. We'll look at this in a couple of slides, especially because we don't usually draw them. So at the place where your reaction's occurring, draw your hydrogens so you know that they're there. If you don't show a hydrogen bond breaking, it is there. Usually we're following our leaving those 4 key patterns. So for example, here we have nothing going on. But I don't really like this rule being follow the key patterns. More of this rule of what's happening here is this might be a source of electrons, but this is not a sink. There is no partial positive charge on this carbon. What would be the reason for these electrons to be even attracted to this carbon? There's none, because there's no partial positive or positive charge on this carbon. Also, this is representing the formation of breaking the octet rule, because this has 2 hydrogens. Now, if this had a carbocation on it, it would be a sink, and it could accept electrons. But it doesn't. So I don't really like this rule in the book about following the 4 key patterns. It's not really that you're breaking the 4 key patterns here. It's just there's no reason for this to react with this. There is no functionality of this carbon. This carbon is unreactive to any nucleophile. There's no leaving group. There's no partial positive. It is the only thing that this carbon would do is a radical reaction, and we haven't talked about that yet. So looking at this, filling in your arrows is pretty easy when you have the resulting products or the resulting intermediate products there. So it's a lot easier to do that. It's a little bit harder to figure out what each step is likely to be, but you work up to it. So first off, I color-coded this because it makes it a little bit easier to see what bonds are breaking and forming, especially when you have a bunch of oxygens. So first, what we have is a negative charge on an oxygen. So all of these oxygens have available electrons. So we have available nucleophiles, and we have an electrophilic center. So that's the first thing to note, is we have the partial positive. And it's a pretty strong partial positive because that carbon is attached to 2 electronegative oxygens, not just 1. So this molecule will behave differently depending on what we're reacting it with. So we're reacting it with a base. So does the base have an available proton? No, it's a base. It's not an acid. An acid has an available proton. So if we take this, and if you're not even looking at this, if you take this and you react it with a base, where is it likely to react? Where is there a place that can accept the electrons of a base? On the carbon, because it's only partial positive. Technically, this is a partial positive, but this is the most partial positive, because it's attached to 2 oxygens. Now, here we're showing the intermediates, and what we're showing is we're forming a new bond between oxygen and carbon. We're also showing that to form the new bond between oxygen and carbon, we have to break a single bond somewhere. We have to break a bond. Because carbon can't have 5 bonds, can't have 10 electrons. Now you might wonder, well, why doesn't this just leave as a leaving group? My answer to you is, we learned you cannot have an SN2 reaction and an sp2 carbon because of sterics. But we learned that. So when you're first writing unreasonable mechanism, you might put that. But the reason why it's not reasonable is because we learned that would be too high energy. So what happens is this electron is where we have a source, and it's going to go to our sink, but we got to push those electrons so we don't have 5 bonds to carbon. Oh, I guess I'm drawing them. We have to push those so we don't have 5 bonds to carbon. That gives our blue oxygen a negative charge. Now, our oxygen doesn't want a negative charge, so we're going to reform our pi bond. To reform our pi bond, something has to be kicked off. So in this particular step, we're showing the green oxygen as the leaving group. Notice my base of my arrow is on an electron. It doesn't matter which of the lone pairs, they're all available. And forming the pi bond between blue oxygen and carbon, which shows that the arrow is on the sigma bond representing the pi bond forming. Then this one is leaving. You might wonder, why is this one leaving and not OH? Well, because if OH leaves, that just shows the starting material. So that's not showing the forward mechanism. When we look at this in chapter 21, we're going to learn that this is really in equilibrium and we have to do things to drive it forward. Because yes, once that OH attacks, it could leave and then we'd reform our starting material. So we're trying to usually draw our forward reaction with our mechanism. But this is a highly reversible reaction when we learn about it in chapter 21. Right now, we haven't really talked about how esters react yet. So, this arrow does form the products that we have shown. Now, our last step is showing just a proton transfer, because that's what this is showing. So we can show that. Now remember, we can't just show our hydrogen being, the electrons being donated to the hydrogen in the form of bond. We must show that bond breaking and going into our oxygen. Now there is a resonance structure we could draw of this. We could continue and go on further. So this is just putting in the arrows for what we see. So let's talk about some common mistakes. Because I think, and then we'll look at some examples and actually draw the mechanism of some things that you haven't seen. So common mistakes, backwards arrows. The base of the arrow coming from a sink. The base of the arrow can't come from a sink. So these all show that. This one's pretty straightforward. This is a partial positive hydrogen. It can't give up its electrons. It doesn't have any because it's partial positive. Also, it's a hydrogen. It literally has no electrons because all of its electrons in the shared bond goes to the oxygen. There's a couple of things wrong with this. One, what this would be showing is a new bond between hydrogen and nitrogen. It's not showing this single bond breaking. So that hydrogen would not only be giving up electrons it doesn't have, it would be forming a bond between nitrogen and oxygen with 2 electrons. And the only time hydrogen will do that is with a boron, and that's weird. And it doesn't go through this mechanism. You actually have the base of the arrow on the on the bond. Now there's a lot of things wrong with that. Also, this nitrogen, lone pairs don't have to be shown. You should recognize there's 2 lone pairs here. Draw them in. That nitrogen cannot accept 2 electrons. It already has 8 electrons. So if it did accept 2 electrons, we'd have to break some sort of bond, and we're not showing any arrow doing that. This one, again, our oxygen already has 8 electrons. It can't accept electrons. It's not a sink. I don't know why I just did that. I'm sorry. There you go. But also, if this oxygen lost this pi bond, it would give it an O+2. So it can't really do that. You can't really donate those electrons. Pi bonds between 2 carbons, it can kind of give up its electrons in the right conditions in this face of a strong electrophile. But if we look at the polarity of this, this is partial negative and partial positive, so it's really unlikely we'd form an even more positive charge on a partial negative oxygen. And then here, again, even though our nitrogen has, actually this nitrogen doesn't have a lone pair at all, and it has a positive charge, so that's really unlikely. So that's our backwards arrows. Our base of our arrow is coming from a source, not coming from the sink. The sink is where the arrowhead points. The next thing is not enough arrows. Every arrow in our mechanism must represent something. So this is an example of the directionality of the arrows is fine. There's nothing wrong with that. This hydrogen could be decarbonated. This is our base. This is our leaving group. Well, what are we missing? We're missing where these electrons are going. We know our hydrogen can't form 4 electrons. So we are missing the formation of this pi bond, which needs to happen. Otherwise, what we'd form is a really high energy compound. So keeping track of where your arrows start and terminate will really help. Also notice in all of my mechanisms, my arrows are going in one direction. Even in our cyclic transition states, they went in one direction pretty much. Meaning they're usually going in the direction of from a place that has electrons to a place that can't accept electrons. So without this arrow, what we're actually showing is this, and this is really implausible. So what we're missing is that arrow. So the correct mechanism and yes, you've seen this elimination before, but you're still always thinking about these things, even if it's a mechanism that you haven't seen. I don't know why it keeps on doing that. And I don't want to put my base of my arrow going to my bond. It's going to, to my carbon. It's going to my bond. So this would be wrong, because that's showing it forming a carbanion. This would be the mechanism that we're trying to drop, and then of course those products would be and this is something that could happen, so that makes sense. Another big thing, losing track of the octet rule, especially for compounds that have lone pairs that aren't being shown. That's another one. So here, our NO2 is kind of weird because it always has a charge. This has a negative charge and this has a positive charge, so this might seem reasonable, but it's not reasonable because nitrogen cannot have 1, 2, 3, 4, 5 bonds, which means it has 10 electrons. Now, if this was phosphorus, that would be different, but this is nitrogen, so this is incorrect because we're losing track of the octet rule. Same thing here, this has our positive charge, but remember, it has a lone pair, so there we go. You can avoid this by drawing in your lone pairs and counting your electrons. If it's in the second period, it should not have more than 4 bonds, or 3 bonds in a lone pair, or 2 bonds and 2 lone pairs. You get the point. No more than 8 electrons. Carbon will have 4 bonds. With the same way, another way you can easily lose track of the octet rule is losing track of your hydrogen atoms. So here, this is not acceptable. This is not acceptable because just because we're not showing the hydrogens does not mean they're not there. This looks fine, but it doesn't look fine if you draw your hydrogens in. Because we don't have a charge here, which means this has 2 hydrogens. And we didn't show anything breaking those hydrogens. So that means we still have 2 hydrogens. And that is 5 bonds to carbon. Now you might say, well, let's just show this breaking. Arrow-wise, fine, we're not breaking the octet rule, but hydrogen is not a good leaving group. H negative, our hydride, will only form if hydrogen is bound to something more electropositive than it, like a metal, sodium hydride. So otherwise, we're not forming an H negative. So we have 5 bonds to carbon here. This is very common. So draw in your hydrogens where your reaction is occurring. Because this carbon is not a sink. What we can do is take this pi bond and put it on the oxygen to leave a carbon cation. That would be fine. But this is not acceptable. Also, that leaves the oxygen with the 2+. That's also really unlikely. It would be more likely that the electrons would be attracted to that oxygen P. So, instead of going away. Just notice, in our correct mechanisms, our electrons are attracted to a sink. So, we don't have a sink. This one can sometimes be a little difficult. Not using a proper source, not using a good source. And usually it's not really one that's going to be as important, or maybe not as important, but as in this class, something that we're going to be seeing as much. Because when something happens that we may think takes too many arrows, usually it's backed up by experimentation. So this particular one is usually one where experimentally it tells you something different. So based on what we know, our nitrogen can give up electrons, that's fine. And it's left with a positive charge, nothing wrong with that, not breaking any rules. Even nitrogen likes acting as a base, that's how it rather does act. So this actually makes sense. Hydrogen is being removed, and then we're showing a new oxygen-carbon bond, but it's more likely we'd form the O negative than having those low electrons from the oxygen-hydrogen bond go straight to our partial positive carbon. So that's where our source isn't quite right. But let's say that for some reason experimentally it was found that oxygen didn't form a full negative charge, then maybe this might be okay. But it's not really the best source. A better source, and this is more a way to follow the electrons, would be the lone pairs forming onto the oxygen and then this lone pair donating. Because it's much more likely that instead of this electrons in this bond being directly given, that it would instead go to oxygen. And this would only be because experimentally, it was shown that this all happened in one step. Maybe kinetics showed that this was a reaction that was based on all 3 of these compounds. So it's a third order reaction, so you might come up with this mechanism. If I was drawing this mechanism, I'd probably just assume we deprotonate to form my alkoxide, and then it would attack. So, like I said, this one's a little bit harder to spot. Not as easy as some of the other ones. And really you need some type of experimental backup typically. Like if I said, write this mechanism, it was found that the first step was third order in all 3 reagents. That would mean they were all participating in the first step. So you'd need a bit more background to elucidate this mechanism. And sometimes you do. So in my advanced class, when we do advanced mechanisms, I give them experimental details to help them write the best mechanism. So at this point, I don't really expect this particular one to be as much. As long as it's an available source, and then when there's weird things that happen, we usually discuss them in class. Things that kind of are a little bit more detailed. Another big one, and you should recognize this one, and I've talked about this one in class, mixed media. Your first rule in lab is don't mix strong acids and strong bases, because they react real fast. And that's true when we're writing our mechanism. If we have an acidic media, we're not going to form a strong base in it. If we have a basic media, we're not going to form an acid in it. So that's mixed media. So for example, a hydration of our ketone, it's very unlikely that what would attack is a hydroxide. Because if any hydroxide was present, it wouldn't attack. It would just react with our acid. So what's much more likely is water attacks neutral and then you deprotonate it. And we talked about that kind of today and when we looked at our epoxide. So if it's under acidic conditions, especially a strong acid, we're never going to form negative charge, a full negative charge, except for on our conjugate base, because our conjugate base is not a strong base, though. It's what makes it a conjugate base of a strong acid. This is a very strong base, so this would not happen. If it even formed, it would react so fast it would be negligible for the overall mechanism. So more likely, water would attack as neutral. The first step is fine. That would be what we expect. But once we form this, what would be way more likely is our neutral water would attack, pushing our electrons, not our hydroxide. And then we would have a deprotonation to reform our acid because this is a catalyst. So that would be much more likely we're not forming negative charge. So I often will see this where a student will deprotonate an alcohol before they show an attack. That's not likely. Also, you have to have something strong enough to deprotonate an alcohol. Remember your acid-base reactions and your equilibrium. If there's nothing strong enough in our reaction mixture to deprotonate an alcohol, it's not going to happen. In the same way, and let me move these little drawings I just did. I'll put it up here. In the same way, if we're doing something under basic conditions, we won't form a strong acid. Now technically, if we're forming a strong base in the reaction, we'll consider that basic conditions. So if this leaves, it's forming a strong base, it's really unlikely you form these two things. So that would be too high in energy. So mixed media. If we're using basic catalysis, we're only forming negative charge. If we're using acidic catalysis, we're only using positive charge. Any strong negative charge, full negative charge would form would just react with our acid. Also, another one, this one's really common, too many arrows at once. That would cause a really high energy transition state, and that would be too high of an activation energy. I often will see students try to put different steps together. That is incorrect. You will form your intermediates. There are some concerted reactions that we discuss, and we discuss why it's concerted and how we know. But if we look at this example, this is really unlikely. It is really unlikely that as we are deprotonating this, we would form a pi bond, which would cause the carbocation rearrangement and push this out while we're making it a good leaving group. That's really unlikely. We might make it a good leaving group, which might activate other stuff to happen, but we will not have this all happen at once. Often, I've seen this most, because we often will use acid to make something a good leaving group. You cannot show a nucleophile attacking while your alcohol is becoming a good leaving group. That's really too high in energy. The only reason why your nucleophile can attack is because your alcohol is a good leaving group, so that must happen first. That's what catalyzes the reaction. So having too many things happening at once is unlikely. That would lead to too high transition states. That would lead to very slow reactions and an activation energy that's unrealistic. So shortcuts are not good. Watch out for them. Unless if some of your arrows are depicting resonance, like the example I showed earlier. If it's resonance, that's fine. This is not resonance. We won't see a transfer occur unless it can form a carbocation. So for this mechanism, the most likely thing that would happen is we would protonate this first. Then it would leave to form a carbocation. Then maybe we'd have a rearrangement. Then, so this would be a reaction that we'd have multiple steps with. So now that we've talked about all those things, and we've talked about what to watch out for and what to do, now we're going to look at an example. So we haven't seen this, though we have just saw the epoxide today, but we haven't actually seen this react with something like a thiol. So the first thing we want to do is look at our substrate, find our regions of electron source and electron sink. So on just our epoxide, where do we have a source of electrons? Our oxygen. Where do we have a sink? Where do we have electrons at? Our either carbon, because in this case both. Neither is going to be more stable than the other. Now we look at our reagents. We have a thiol. SH also has electrons. Thiol is right under oxygen, but thiol is a little different than oxygen in that it's not a very strong base, but it's a great nucleophile. We also have H2SO4. So that means we have acidic conditions. Since we have acidic conditions, why won't my thiol attack first? What would happen if my thiol attacked first and we opened up the ring? What would that form on the oxygen? A negative charge. We won't form a negative charge in H2SO4. The acidic conditions. So our most likely thing to happen first is a proton transfer between my oxygen and my acid to make my oxygen a good leaving group. Because again, if H2SO4 wasn't here, the thiol could attack. So we have to look at what's in our reaction. So I'm going to draw my H2SO4 because I like to see what that looks like. H2SO4 is a great base. It's not a base. I'm sorry. I've been talking for 4 hours now. H2SO4 is a great acid because it's non-nucleophilic. So it's used a lot because it's a great source of proton, but it won't attack as a nucleophile. So some acids, like our HCl, also a strong acid, but our chlorine negative is a great nucleophile. So that can cause problems. So H2SO4 doesn't have that problem. So we'll have our proton transfer. It doesn't matter which of those electrons you show from your lone pairs. So now we have, and you must show it, a formal charge on our oxygen. And that's going to make our oxygen a good leaving group. Now, our thiol can attack. But remember, our thiol is not going to attack as a negative charge. Why? Why won't we deprotonate the thiol? Again, we have acid, so it's really unlikely that anything would deprotonate the thiol. Because we don't have a strong base strong enough to deprotonate our thiol. Because our conjugate base of H2SO4 is not really a base. Our oxygen isn't really basic enough to deprotonate that. If we look at our equilibrium of the deprotonation, we'd form an O plus and an S negative. So the backwards reaction would be favored. So our thiol will attack neutral. Which of those two carbons it attacks? In this case, it's irrelevant. I'm labeled it as 1 just to be consistent with my final compound, but it doesn't matter. So my thiol is going to attack, and then what's going to happen? Yep. Why not the bond between carbon 1 and carbon 2? Carbon's not a good leaving group. So that opens up the reaction, but we're not done with the mechanism because that leaves a positive on our thiol. It's our bond. So our last step is something coming in and deprotonating that thiol. What's likely in this reaction to deprotonate that thiol? Maybe another molecule of the epoxide, maybe our conjugate base. Something, I don't even care. I'm okay with you putting base. But something is going to deprotonate that thiol in the reaction mixture to form our neutral compound. So technically this is a new reaction, but we did kind of start with epoxides today. Any questions with, and the way I'm talking about this is how you should be thinking about what's going to happen. You should be finding your partial positive, partial negative charges. You should be finding your sinks and your sources, and you should note if there's any acid or strong base present before you start. That's very important. And the more you practice, the better you get. And don't put a lot of mechanisms in the homework, because the mechanism tool on the homework is really annoying. And then you spend more time trying to figure out how to make it do what you want it to do than actually learning that you're doing it right. So you've got to practice these because they will be part of your exam. I really recommend the solutions manual for the second edition, because the solutions manual in the first edition doesn't explain very well. I really recommend writing them and going back and check. And writing down the mechanisms, because the homework, you can do the mechanisms assignments for bonus and they're great. And they give you feedback right away. But I'm testing you on your drawing, so you have to be able to write it. So the more you practice writing it, the better. Okay, so now we're going to look at one that's a lot more complicated that we definitely haven't looked at. First thing to note, what are the conditions of this reaction? Acidic. So we will not be forming any strong negative charge. So no negative on the oxygens, no negative on the carbon. That would be strong bases. That's the first thing to note. The next thing is, again, we have an oxygen in our substrate that has lone pairs. And we have a partial positive carbon. So we have a sink and a source. So the question is, what is it going to act as first, a sink or a source? And the answer is, it's going to act as a source first because we have the acid. So really just because we have the acid there. So that's going to be our first step, because we won't form any negative charge. So we can't get the attack on the partial positive carbon. If we did, that would push the electrons on the oxygen, giving it a negative charge. That's not going to happen in an acidic solution. So the first thing is going to be that proton transfer. Often, when we have an acid catalyst, the first thing is proton transfer. Don't memorize that. There's a reason for it. Understand it, but that's often what's going to happen. And this is kind of a long one, but we kind of repeat the same thing multiple times. So I'm going to try to write it kind of small. I always run out of room for this one. Don't forget your positive charge on oxygen. So now we have a positive charge on oxygen. That is what we call activating our ketone. Because now when something attacks our carbon center, our partial positive carbon center, it's going to put the electrons on our oxygen and make it neutral. So it activates the reaction. Also note, you might wonder, how can we attack that partial positive carbon with that ring in the way? Remember, our sp2 carbon is planar, so it's actually attacking not quite under like we show it, but it's actually attacking a bit above or a bit below the plane. So just a side note there. We don't have to worry about sterics because it's trigger planar. I mean, there's some sterics, and we'll talk about that when we get to chapters 20 and 21, but it's not as much as you might think based on the two-dimensional drawing that we have. And remember, our cyclohexane ring is likely in the chair form. We're just not drawing it that way, but it's the way it's going to be. So now that we have this activated, do we have a nucleophile in the reaction that can attack this partial positive carbon? It doesn't need to be a strong nucleophile because we have this activated thing. So what else in our reaction mixture is a source of electrons? The pi bond in this case isn't a source because now our oxygen is positive. So if we gave up these electrons to something, it would leave us with a positive 2. So that's not a source. And often our pi bond between a carbon-oxygen double bond is not a source anyway. Because for it to be a source, because we have that polarity, it would have to, again, leave a positive charge in the oxygen. So oftentimes, for a carbon-oxygen pi bond, we see that as a sink. Now, a carbon-carbon pi bond is not a sink because we don't have any partial positive or partial negative. So it acts as a nucleophile, but a carbon-oxygen pi bond has that partial positive carbon. So that's more of a sink, and not typically a nucleophile or for the pi bond. So just because it's a pi bond doesn't mean it behaves the same way as the pi bonds we've been talking about. Our carbon-carbon pi bond is a completely different functional group than our carbon-oxygen pi bond because of the polarity. What else is in this reaction mixture that has lone pairs? The thing on top, our diol. It's a dialcohol. So our diol has electrons. We have two oxygens that have lone pairs. Which one's going to attack first? It doesn't matter. One of them's going to attack. I'm going to redraw it over here just for it to be clear. Now remember, we're not going to deprotonate that first to make it a strong nucleophile because we have acidic conditions. First, we don't have a base anywhere in this reaction that can deprotonate an alcohol. Because remember, we need a pretty strong base to deprotonate an alcohol. At least hydroxide or stronger. We don't have a strong base in this reaction. Also, even if we did deprotonate our alcohol, it would just react with H2SO4. So this is going to react neutral. One of the high oxygens, it doesn't matter which one, eventually both of them are going to react. And we're going to show one at a time. So it's going to react with our partial positive carbon, and remember, we got to push electrons onto our oxygen. That forms this neutral OH and a new bond between our carbon and our oxygen of our diol. Now note, we're left with a positive charge. So our next step is going to be deprotonating. There is the possibility, because this is an acidic solution, that our oxygen that's directly next to our OH, that's directly next to our OH that has positive charge might take it. And that's likely happening in some of the reaction, but I'm not going to show it that way. I'm just going to show it being deprotonated. And then my H2SO4 protonating. But really, it could. And what's this base? This reaction is going to have a buildup of water, so it's likely going to be water. So I'm not actually even being specific about that base. Because there's a lot of things in this reaction, because it doesn't take a strong base to deprotonate an OH positive, because that reaction is going to be forward favored. So now we have this intermediate structure, but that's not our final compound. And I'm going to just kind of hint to you what needs to happen. So this isn't our final compound, because our final compound has both oxygens of the diol now attached to this part. So what's going to happen next? Well, we're clearly going to need our OH to leave. Why don't I just do this? What's wrong with that? Because then I'd form OH minus. I'm not going to form OH minus in acidic media. So instead what's going to happen is I'm going to have the proton transfer to make OH a good leaving group. Because OH is not a good leaving group. In these conditions, it's absolutely not a good leaving group. Not in acidic conditions. We will not form a strong negative charge in acidic conditions. Acid catalyzed reactions typically have multiple proton transfers. So our next step is going to be another protonation. Again, we still have our H2SO4 floating around everywhere. So now we're going to have a good leaving group. I don't need to draw my lone pair that's left, but I do need to draw my formal charge. Now, we can get the attack of our second alcohol of our diol. How do I know it's this and not another molecule of our diol? Well, because that's not in our product. But also, the intramolecular reaction is going to be faster. This forms a 5-membered little ring, so that's pretty stable. And this alcohol is attached to this reaction center. So intramolecular reaction, where this is going to react with itself, is really likely because it's closer together. It doesn't have to find each other. So this particular reaction, because of the fact of this size, and we'll see in chapter 21 that we specifically use this as a protecting group to protect our acetyl guano, because it can be removed in the reverse reaction of what we're drawing really easily. So we'll learn about that later. But right now we're just drawing the mechanism. So now we can get that attack, our nucleophilic attack. And now we can have the loss of our leaving group. We're almost done with this mechanism. Not quite yet, but almost. Oops, that's supposed to be dark. It almost looks like our final product, except we need to do our final deprotonation to remove that hydrogen from that alcohol. And that'll form our final product. And again, we have water floating around, so it's likely just going to be water. And remember, H2SO4 is dissolved in water. It's not, you can get as concentrated H2SO4 as you want, but there's going to be some water in it. So there's likely going to be water floating around. That just reforms our H3O+. So reforms our acid. We don't have any more acid at the beginning than at the end, or any less. So that is our mechanism. Notice no negative charge is forming because this is acidic media. Notice that we're not trying to do too many steps at once. That's a key problem. Okay, I have one more if y'all want to watch one more. This one is a reaction we won't even look at. This isn't one that we're going to learn. This is one I've done in advanced organic a lot. But it doesn't matter. We should be able to figure out what's going on. I need more room, so I'm putting it up. Okay. I don't even need this. So here, first thing to know, what condition is this under? Basic. So we're only going to be forming negative charge. So this one's a little bit different. We can't protonate our alcohol first, our oxygen first, because we don't have that. So this one's going to be a little bit different. So we're under basic conditions. What we want to consider, well, it's really unlikely, first off, we just talked about how Br2 is an it can be an electrophobe. And we do have available electrons on our oxygen. But it's really unlikely our oxygen would attack, because that would leave it with a positive charge, and this is basic solutions. And that's not where our bromine's going to be anyway, but that's not really, in this case, that's not really clear for the end product. What you might think the end product would be is our oxygen attacking, but carbon is not a good leaving group. So this one's, like I said, a little bit more complicated. It's a really interesting reaction. It has to do with basicity and the acidity of our proton. So we have a base. The first thing, since we have a base, is where's our most acidic proton? We don't have a hydrogen on our oxygen. That would be our most acidic proton. But if you look back at the pKa's, this hydrogen, because it's alpha to our acetyl guano, which means that negative charge will be in resonance, actually has a pKa of about 20. And that pKa, and this one does too, but that one is more sterically hindered. So we're going to assume we're going to react with the end one. So the pKa of those hydrogens are about 20. And that is a good enough pKa for our hydroxide to deprotonate. So I'm going to show that. And what I'm going to show is, well, first, let me just side note. if we deprotonate this, we're going to form this carbanion. And then we have our resonance structure, which stabilizes our negative charge. So in this mechanism, I'm going to show these two steps happening at once. You don't have to. You can draw the resonance structures, which would be this, but for space, and really this is about space in this case, I'm going to show my most stable resonance structure right away. So just keep that in mind. So our most acidic proton is going to be that hydrogen on that alpha carbon. I don't care about the sodium, it's just our counter ion. So our first step, and again, I'm going to show, these arrows are just showing the going to my most stable resonance contributor. You could show the carbanion and then the resonance structure, and that's fine, but for space, I'm not going to. So what we form is this structure. Now we have a pi bond that's able to act as a nucleophile. That can act with our Br2. That we just learned is polarizable. And put this as which can have a partial positive and partial negative charge in the right conditions. And these are the right conditions. So I'm going to reform my pi bond, making this a very strong nucleophile. And what I'm doing is now I have this. Now here's the thing about this reaction. It's really hard to stop here. And the reason why it's hard to stop here is, remember, base is still floating around. What can you say about these protons now and their basicity? Their acidity. Remember, what makes our negative charge more stable? Resonance, but what's the other thing? Aereo. Atom, its own carbon. Resonance, what does I stand for? Induction. I put a bromine on a carbon. Now my pKa of that hydrogen that I just deprotonated in the first step is now even more acidic. And remember, the difference between 17 and 20 is 2 orders of magnitude. 2,000. This is 2,000 times stronger than it was before. So now I can't stop this, and I'm going to have another deprotonation. And basically, this is going to happen 3 times. So in this case, I'm not just using what I know about my curved arrows. And I'm not just using what I know about stability, I'm also using what I know about acid-base chemistry, which, as an organic chemist, acid-base chemistry is so important. Because we not only use acid and base catalysis a ton, but we form strong acids and strong bases all the times in mechanisms, and we need to think about how they react. So, again, I have another pretty good nucleophile. So I'm going to have that nucleophilic reaction happen again. And I'm showing the reformation of the carbon-oxygen single bond. Because, double bond, because it makes more sense. If I didn't, the pi bond would leave that carbocation, and then it would form the resonance structure. Because a negative charge oxygen next to a positive charge carbon, it's just the resonance structure. So I'm showing it all happening at once because our most stable contributor is the oxygen-carbon double bond. So what I'm saying is, here's this. If I just drew, here's my electrophile. I would be drawing electrophile again. It's my electrophile. And this is a carbocation, my more stable resonance structure. Would be this. So I'm just drawing the resonance happening at the same time. Oh, forgot my electrophile. So I'm just drawing this all at once. You can draw it separately, but your more stable resonance structure is going to be the one with no charge. forms a second carbon-bromine bond. Oh, you didn't show it. Now guess what that did to this hydrogen that's still left? It's even more acidic. My pKa is now closer to 15. So I can't stop my base deprotonating this again. There's no way. This particular reaction is a specific reaction that under basic conditions, you cannot get the one addition of halogen. It will keep on going. So we will have another, because remember, this is basic conditions, so we're not removing the base is still there. So we get, again, another deprotonation to form my pi bond, pushing my electrons onto my oxygen. That's why we call it electron pushing, because often it's a chain reaction. So now we can get one more addition of that bromine. And we almost have what looks like the final product. Not quite though, but almost. So now, we don't have an acidic hydrogen. We do still have our OH floating around. OH negative is a strong base. What else is it? Strong nucleophile. Here's the thing. Now this carbon, super partial positive, because now it's next to 3 bromines. And carbon is not typically a good leaving group. However, CBr3 is a good leaving group, because that carbon's negative charge can be stabilized really well by 3 bromines. Not 2 bromines, not 1 bromine, but 3 bromines it can leave. So now our oxygen is actually going to act as a nucleophile, forming one more intermediate. I'm going to put it over here because I almost had enough room. We're going to put it in blue now. And now we're going to reform our pi bond. And this thing's going to leave. So we're actually forming this. And if I was really nice, I'd show that compound. Because really at the stage you're in, you would probably need to see that compound formed as well for you to really follow the mechanism. I really wouldn't expect you to guess at that right away. Not at your level. At my level, I should be able to look at that and figure that out. But you have to you're using what you learned. This is why Organic 1 was all that background. Because you can apply that background to everything we do. Acidity, our electronegativity, all of that. That's what we're doing. So that's it. One more thing. I didn't show this attack in this lead because, again, we don't get an SN2 at an sp2, an SN2 reaction at an sp2 carbon because it's too, there's too much sterics. So we form this tetrahedral intermediate is much more likely. And that's what we'll see throughout a couple of reactions we do. We won't ever do this particular reaction, but because I kind of skipped this chapter, I never have time to cover it, unless if for some reason we have time to cover this chapter. But I usually end up skipping the chapter on the alpha carbon of our ketones. But this is the kind of reactions you find. If I gave you this mechanism, I wouldn't give you this on a test, not at this level. But if I give you this as like a bonus at some point, I'd probably have to give you this as well so you could actually see that that's forming as well. Because I don't really expect you to see that now. So this is a really complicated one, above the level where we are, but this is by the end of the class where you should be able to get at by thinking about what's going on. And it takes practice, it really does. So the more you practice, the better you'll get. Does anyone have any questions? So that's pretty much what I have, unless if anyone has any specific questions about mechanisms. I hope that was helpful. I am now tired, so I'm going home, and I will not be available for the rest of the day.